So this video is one of three to do with something in chemistry called Hess's law. Now, Hess's law is something that initially some people do find challenging, but often people get themselves won over and actually end up finding this a relatively straightforward thing to do, unless it is the examples from the final video. So what is Hess's law? So Hess's law is a principle that states the total enthalpy or energy change for a chemical reaction is the same regardless of the pathway taken to get there. So the diagram we've got on that slide, if we were doing a reaction and we were taking reactants A and turning them into B, that would have an overall chemical change. And they've said that that's delta H1. That value would be equal to the energy change if we had chemicals A, we turned them into chemical C, and then turned chemical C into chemical B. Because we started at A and ended at B, the overall energy change must be the same. Or we could take chemicals A, turn them into chemical D, then turn chemical D into chemical E, and then chemical E, turn that into chemical B. Because we started at A and ended at B, the overall energy change must be the same. So the energy going from A to B, whether you take root 1 or you take root 2 or you take root 3, because you're starting in the same place, ending at the same place, the total energy is exactly the same. That is because of bonds. Going from A to B, all the bonds that you break in A and all the bonds you make in B, it doesn't matter what way those bonds got rearranged in the process, it's still going to be the total energy change is the number of bonds in A minus the number of bonds in B. And so this leads us to being able to do certain things and certain calculations. The first set of questions we've got are all going to have to do solely with diagrams that look like that one at the top, just a bit simpler. And they are usually going to be multiple choice questions. So we have a question here. We're wanting to know what the value of X is. So X is going from A to B. So going from A to B, well, going from A to B would be the same as going this whole route there. So X is A to B, so the alternative route is going from A to C, then from C to D, and then from D to B. Now if we look, we can go from A to C, that's plus 76 enthalpy change, and then from C to D, that's easy, we can do that, that's minus 110 enthalpy change. The issue is, we don't have the energy change from D to B. We have it the other way round. Our arrow is going the wrong direction. And so what we have to do is flip the arrow. But if we flip the arrow, we also have to flip or change the sign on the enthalpy change. So B going to D was plus 95. So if we're going the opposite direction, but the same path, it's negative 95. And all we do is we add all those numbers together. So 76 minus 110 minus 95 gets us minus 129. We have a past paper question, and again, it's work out X. So give yourself a bit of time, pause the video if you need to. But X is going here. The alternative route would be going there and then going that way. So this number is correct, but this one, the arrow's the wrong way. So we would have to flip the arrow, meaning we need to change the sign. So it's going to be negative 194 plus 283, which is going to be negative 111. One is an example where instead of numbers, they have algebra. Now in this one, the multiple choices, all of them start off with B. So we are wanting to do B. We're wanting to go from W to Z. Our alternative route is this, and then this, and then this. So our first route is A. A is fine. Second route, arrows going the wrong direction. So from X to Y, we just call it C. We're going the other direction, so that's going to be minus C. Then from Y, we're going from Y to Z. The arrow's the wrong way. So we need to change the sign so it becomes minus D. So in all of them, just look at what we're doing to the arrows. If we flip the arrow, we're just putting a negative sign instead of a positive. So our answer becomes A. In the next videos, we'll look at situations that don't use diagrams, and instead we have to match actual chemical equations to a target equation, which is a little bit more complicated, but ends up more straightforward than you think.